So far we discussed about D flop and how it gives one clock pulse delay, and the same when it's copied, captured at another edge gives half clock pulse delay. And now the main concept in solving frequency dividers is a mod n counter, a modulus n counter. Basically it's an asynchronous counter. Asynchronous is nothing but like if I consider a circuit, all the devices in the circuit are not given the same clock. Only the first device is given the clock and remaining devices get clock from the first output or somehow, but all the devices are not given the same clock. So it's an asynchronous counter, and the sequence, I mean like modern counter counts from sequence. So starting from 0, it counts till n minus 1. So it counts till 0 to n minus 1, and after n minus 1 again the same sequence repeats. So if suppose let us consider modern counter. So let us consider mod 3 counter. Mod 3 counter, it counts from 0 to n minus 1, where n is 3, so 0 to 2. It counts from 0 to 2. So let us suppose the initial value is 0. After first clock pulse, the count becomes 1. After second clock pulse, count becomes 2. After third clock pulse, again count becomes 0. Means, if you consider a modern counter, after n clock pulses, we are getting the same sequence, 0 and again 0. Means after n clock pulses, means after 3 clock pulses, again we are getting 0. So the sequence is repeated. After 3 clock pulses, again, if it is 0, 1 and 2, again 0, 1 and 2, and like this, so on and so forth, the sequence repeats. So now to design this counter, so I am taking this particular example. So based on this example, you should be in a way to solve any mod counter. So first question to answer this before designing a mod counter is how many flops it has. See, there are two ways of approach. One is formula based and one is logically. See, for example, in order to represent mod 3 counter, so it counts from 0 to 2. So to represent 2, how many minimum number of bits are required? So obviously 1 0, it's 2. You can also represent this in this. You can also represent like this. You can also represent like this. But minimum number of bits, how many? There are 2. So each bit 1 flop. So 2 bits, 2 flops are required. Logically you can get this. So and similarly mod 7 counter, minimum number of representation, mod 7, it counts from 0 to 6, 0 to n minus 1. So in order to represent 6, what are the minimum number of bits? How many minimum number of bits are required? Obviously this is enough to represent 6. So 3 flops are required. Similarly mod 10, it counts from 0 to 9, 1, 0, 0, 1. 4 bits are required. So first question to be answered is how many flops are required, and thereby we can solve very easily. And this is a synchronous counter, means only first flop gets the clock which we are giving, and the next flop gets the clock from the first flop output. So in this I'll also make you clearly understand like whether to take the next flop as positive edge or negative edge, so on. Many doubts, I'll clear you. So for example, we are taking here mod 3 counter. So for every 3 clock pulses, the sequence repeats like we discussed here, 0, 1, 2 and 0, 1, 2, so on and so forth. And formula based 2 power n greater than 3. I mean, formula based how we will solve this is 2 power n greater than that mod value. For example, we are taking mod 3, 2 power n greater than 3. So n should be 2 only, because 2 power 2 is 4, 4 is obviously greater than 3. So this n is nothing but number of flops. So if you don't want to remember or mug up this formula, logically you can come to this conclusion that how many flops we require. So this formula base I did, and I required 2 flops. And now this. So for example, if you take so for mod 3 counter we require 2 bits. So let us suppose this is LSB and this is MSB. 0 0 0 1 1 0. These are nothing but 0 1 2 0 1 2. I am taking this side as MSB and this side as LSB. Normally we will take MSB and LSB. So I am just saying, I am just taking MSB and LSB. So 1 0 is 2, 0 1 is 1, 0 0 1 0 0 1 0 0. So clearly, if you make a conclusion here, clearly you see this should be, this is toggling. This 0 is changing to 1. Again 1 is changing to 0. See, this is toggling, right? Let us suppose the mod 3 counter is that. Let us take mod 5. So mod 5 requires 1 0 0 4. 0 to 4 it counts now. So obviously 4 minimum number of bits is 3. So I am taking MSB, middle bit and LSB. So Q0, Q1 and Q2. 3 bits are required, 3 bits I draw. So 0 0 0, 0 0 1, 0 1 0, 0 double 1 and 1 0 0. And here also you can clearly observe that my first LSB is toggling continuously. And based on this toggling, this is changing, and based on this is changing. So as a designer, the way of approach should be very particular. By this you should come to know that okay, my first bit is toggling continuously, and obviously I should use flip-flop which I am using in my design should be in toggling mode. So by this you can come to a conclusion that my first bit is continuously toggling, so it should be in toggling mode. And from this toggling you can come to know that some phenomenon is taking place here. Based on this toggling only it is toggling. You see, so if you clearly observe this first bit, so it's toggling continuously. So our first requirement is flop in toggle mode. And see, if you can clearly observe this, based on this toggling, it is changing continuously. So whenever it is changing from 1 to 0 only, it is toggling. Whenever it is changing from 1 to 0 only, it is toggling. So you should be in a position to notice, like, based on what toggling it is changing, and based on that you should give that output as clock to next clock. So for the next clock to trigger. So first of all, our requirement is flop in toggle mode. Now let us know, like, what is toggle mode. Toggle mode is nothing but every clock pulse the flip-flop should toggle, in the sense it should change the state from 1 to 0, 0 to 1 and so on and so forth. Let us come to this. If we take D flop in toggle mode, so toggle mode in the sense output should change from 1 to 0, 0 to 1 continuously. So if we consider output Q, I am just representing Q in waveform. So first let us suppose Q is initially 0. So if you draw the waveform of this output, say the initial value is 0. 0 is coming here. But see, what we are transmitting is Q bar. If it is 0, this is 1. So 1 is sent here, and the next clock pulse we get output as 1. So at this clock pulse we are sending 1 here. So 1 is captured, and 0 will be changed to 1, and 1 will be changed to 0. And the next clock pulse we are sending 0. So this 1 will become 0 again. See, I am capturing output only. So by this what you can understand is, every clock pulse the previous state is toggled, in the sense complemented. So 0 is changed to 1, 1 is changed to 0, 0 is changed to 1 and so on and so forth. So the D flip-flop in toggle mode. So this we should use for the LSB bit. See, clearly you can understand that every clock pulse the LSB bit is complemented, toggled. So the first flop should definitely be in toggle mode. So if someone asks, I don't want a mod counter with D flop, can you do it with JK flop or can you do it with T flop? If they ask, simple. You know, when J and K or both are 1 in JK flop, it is said to be in toggle mode. Similarly, T, when T is equal to 1, it is said to be in toggle mode. So you can also use this for LSB bit. And now, we'll come to designing of this counter. See, 0, 0, 0, 1 and 1, 0. This is mod 3. Okay. So in detail we'll discuss mod 3, and by this we should be in a position to design any mod counter. So LSB is toggling, 0 is changed to 1 and 1 is changed to 0. Okay, again the sequence is repeated. So first LSB should definitely be in toggle mode. So like we discussed, this is in toggle mode. Q bar is fed back to D. So this is actually in toggle mode and this is a flop. So now the second flop also it toggles somehow. Somehow it is toggling. So we should be in a conclusion that in mod 5 also we consider it is toggling somehow, but based on this action only. So by this we should come to the conclusion that all flops should be in toggle mode, but they should not continuously toggle. In the sense, this flop should be continuously toggled, and here also it is toggling, and here also it is toggling. But this flop, based on this output only, it should toggle. See clearly, this I am representing here it again. 0, 1, 1, 0, 0, 0. See, 0 is toggled, 0 is changed to 1. But here, when LSB is changing from 0 to 1, should there be any change in MSB? No. So, if we give this particular one like this, means we are giving output as clock to the next clock. So, if Q naught changes from 0 to 1, see this is Poiseuille's representation and this is Negate's representation if you give clock like this. And if you give Poiseuille, every 0 to 1 transition, this will react, this will trigger and this will toggle. And if you give the same as Negate, every 1 to 0 transition, it will toggle. It will be complemented. So, suppose if I give like this, when LSB is changing from 0 to 1, so this is changing from 0 to 1, it got the trigger and this will also toggle. But our requirement is this should not change. So, if suppose I give here negative edge, first of all, LSB is changing from 0 to 1, so it will change from 0 to 1, but we give negative edge to this next flop. So when 0 to 1 comes, it will not trigger because it needs 1 to 0 transition, but we are giving 0 to 1 transition. So this will not trigger, yes or no? Agreed? So now, so no change. Now LSB is changing from 1 to 0, so this transition only no. So what this flop requires is this transition only no. So definitely it will toggle, yes. So it will toggle from 0 to 1. And now what happens in this is, this process repeats continuously, yes or no? Because 0 again it will change to 1 and 0 to 1 transition, but it requires negative edge. So it will not change, so it remains unchanged. Now, our requirement is this mod counter should count from 0 to 2 only, 0 to n minus 1 like we discussed. It should count from 0 to n minus 1. But what it is doing here, to our surprise, it is counting from 0 to 3 and it is continuing. We need to do something such that it counts from 0 to 2 and again it in this place, our requirement is to get 0 and 0. So, we should do something somehow and make flip-flops again clear. In the sense, again they start from 0 0. So now what I'll do is at this stage I am getting this as 1 and this also as 1. So I am taking this state only. Please remember that I am taking this state only. After third clock pulse means 1, 2, 3. At third clock pulse my value of the counter is 1 and 1. And this is MSB and this is LSB. So this is 1 and 1. Somehow I should do something and clear all the flip-flops. Now again, it's a task for designer. The way of approach is very important. We can use anything. So simply, I'll do like this. I'll take this and I'll take this. I'll send both to an AND gate. Clear? Agreed? And this AND gate output, I take secondary input clear. First, all primary inputs, reset is primary input. And whereas secondary inputs are nothing but preset and clear. Clear in the sense, when clear is active, I am taking active high clear because my output of AND gate would be 1. So I can take anything. If I take as negative edge, I can send it to NAND so that output will be 0 and giving to clear of active low, it again clears. So here I am taking positive clear, so I took AND gate. So when both are 1, output will be 1 and this I directly give it to clear pin, secondary input. So obviously what will happen, clear in the sense when clear is active, whatever may be the input, that doesn't matter, output will be 0 0. See, whatever may be the input, but output will become suddenly 0 and 0 and our requirement satisfied. See, now I am saying like there could be n number of ways to solve this problem. Like I told, if suppose if I take here, what if I take here both are ones? What if I take here NAND gate? NAND gate, the expression of two input NAND gate is LB bar. So if one input is 0, obviously output will be 1. If I take NAND gate here, what happens is, when I send 0 0 also, output would be 1. When I send 0 1 also, output would be 1. When I send 1 0 also, output would be 1. But if I send 1 1, output would be 0. To my surprise, what is happening actually and what will mean? See, for 0 0, it should go to next state, at 1 1 only again it should be cleared. But what is happening? At 0 0 itself, it is sent here and again it is cleared, but next state would be 0 0 only. Because 0 0, if I send to NAND gate, what happens? Output is 1. Again they are cleared. They are not running to the next state. Our requirement is after n-1 states, means after 2 only, the next state should be cleared. So that after n clock pulses, again the sequence repeats. So can I use a NAND gate here? No. So what if I use OR gate? What if I use OR gate? Again see, 0 0, if I send to OR gate, output is 0, because clear or active high, it will not work. Okay, satisfied. It will go to next state. 0 1, when MSB is 0 and LSB is 1. Now what happens? It will become 1 and again cleared. After this state, we will get again 0 0. Is that our requirement? No, that is not our requirement. Obviously our requirement is after this 0 1 2, after this counter counting 0 1 2, again it should reach 0. So what I am saying is, clearly identify the basic gate where it satisfies your requirement. It should meet your requirement. See, now I tried with all gates and I came to conclusion that obviously if I keep AND gate only, it will work perfectly. That's what. See, there could be n number of ways. So here, using a basic gate and making a counter after reaching the final state, again clearing it is an important task in this. And please do follow this method. Like, it's not that by heart something, by heart is okay, every time you should use AND gate only. If you use AND gate, like I told, for some other counter, is okay. Let's say this is a mod 5 counter. It will count from 0 to 4. After this, it actually counts 1 0 1. But what is our requirement? This 1 0 1 place we should get 0 0 0, because 0 to 4 it came, and again 0 to 4, again 0 to 4 it should repeat. So 1 0 1. So what should I do this? Similarly, taking active high clear. So what I'll do, I'll take MSB bit, I'll take this bit, and I'll take this bit. I'll send it to an inverter, I'll do like this. Again, I'll send it to an AND gate, and I'll give the clear pin of all flops, and thereby I can clear it. So you should think in some way like, here both are 1, so there is no chance of using an inverter. Here the middle bit is 0. Obviously I need an inverter, otherwise this should satisfy to all the above conditions. It's not that only one condition. It should satisfy this condition, because this condition clear should be 0. Here also clear should be 0. Clear 0, 0, 0. And this case only clear should be 1. That is the best design. It's not that every single state clear should be 0. It's not that every state clear should be 1. If it is cleared, every time flip-flop will be in this state only. Agreed? Yes or no? Every time flip-flop will be in this state only. But our requirement is after passing through 4 states, 0 to 4, next state should be clear. So you should use your mind and design in such a way that, okay, only for that particular thing only, my clear pin will be activated. At that time only, it is cleared. Any counter for that matter. So you should be cleared in making the clear pin active for that nth state. Means if it is for mod 5, after 4, 5 would come, obviously. This one you should make it as 0. If it is mod 7, after 6, 7 would come. This 7, you should make it as 0. You should do something. And you should satisfy for all also. It should not only satisfy for this. If we see, let us take this only. If we send any of these above combinations also, clear should be 0. But only this combination, if I send clear should be 1. That's okay. Let us suppose take this. Let us suppose take this combination. Okay, this is MSP. 1 1 0. Okay, 0 is there. Obviously one input is 0, output will be 0. So it will count next state also. But this state, obviously the output will be 1 and it is given to clear and it is activated. So what you should come to know is, okay, now I will be giving the final conclusions. It only counts from 0 to n-1, that's my first conclusion, and it's an asynchronous one. See, only the first clock is getting clocked and the next clock is getting clocked from the previous output. And again, don't confuse in giving positive edge or negative edge. Like I explained, you just go by truth table. You just clearly mention it. What is it? What is my MSP? What is my LSP? It is toggling. So I use first clock as toggle mode. And based on this, it is also toggling. Based on this, it is also toggling. So every flop I use is a toggle mode only. But when it is going from 1 to 0 only, it is toggling. So 1 to 0 means definitely I give this to neg edge only. Then only it works. So please come to conclusion that at what edge this flop should toggle. Means the successive flop, the next flop should toggle. Obviously this will toggle for every flop, every clock. So 0 to n-1 clock pulses only. After that somehow you should clear it. So please take a clear pin, and at that particular state what basic gate will give output as 1 if it is active high only. If it is active low, which gate will give output as 0. So like that you should think twice, thrice before using this particular gate. So this is modern counter.